welcome to lecture number 36, and we have been discussing how to solve differential equation in time domain when the excitation function is an impulse function. Today I will highlight remember that to show this for example, an RL circuit is there is an impulse applied. What happens and we want to know the current for time t greater than 0, we want to solve the current. Now, for t greater than 0 plus there is no excitation, impulse came at t equal to around t equal to 0 and then also it vanished. So, after that the circuit will be like this here. Now, the question is such an circuit can have an current provided there was some initial current. If there was initial current I 0 minus, which will be known to me. So, what impulse does? It changes that initial current at I 0 plus following this relationship. Got the point? So, this is the point. Now, let me solve a suppose example 1. Suppose you have a circuit where R equal to 4 ohm and L equal to suppose 8 Henry and I will excite this with an impulse. I will excite it with an impulse function delta t. That is what I will be doing. Unit impulse function. See, problem at hand is this one. What will be current? I t, an impulse is sitting at the origin. So, I t will be equal to how much? For t greater than 0 or t greater than 0 plus. For me, there is no difference between t equal to 0 and t equal to 0 plus. So, this is the circuit I want to solve. So, the equation of the circuit will be R I plus L d I dt is equal to delta t. And suppose it is given that I 0 minus is equal to suppose 1 ampere. It is given. Inductor inherited this current because of some previous operations from some other circuit, then suddenly it is connected here. So, I 0 minus is 1 ampere. So, this delta t exists at between 0 minus to t to 0 plus this fellow only exists. For t less than 0 it was not there, I 0 minus was 1 ampere, and for t greater than 0 plus, now the circuit at t greater than 0 plus will look like this. 4 an inductor L and there is no input now, it is shorted delta t, because delta t looks like this. This is delta t and this is time and this is t 0. T equal to 0, something happens. What happens is this one. Now, so for t greater than 0 plus, what will be the equation? I will straight write this 4 plus L d I dt, and that I am allowed to write it to be 0 because now this is for t greater than 0 plus. This is 8 Henry and this is 4 ohm. This is the situation and this current I want to find out I t. Now, to solve this differential equation, I should know the initial condition. What is the initial condition? I must know I I 0 plus to solve this differential equation. How to know I 0 plus? We have seen that I 0 plus will be equal to I 0 minus plus 1 by L, is not that is what we have seen. Now, I 0 minus is 1 ampere. So, 1 plus 1 by 8, 1 by 8 is 0.125. So, 1.125 ampere. Therefore, here is an RL circuit which has got an initial current 1.225 ampere. So, how it will decay? This let me write it as 8 Henry, and then we know how to solve this. This equation is nothing but di dt divided by 8 plus half I is equal to 0. So, I can straight away write I t will be equal to a into e to the power minus half t, and then I will apply this boundary condition. So, at t equal to 0 plus, the current is 1.125. Therefore, the value of A will be 1.125. So, the solution will be 1.125 into e to the power minus half t. That is the thing. That is, impulse at t equal to 0 will change the boundary condition I 0 minus, which was existing just prior to applying the impulse. That initial current will suddenly jump from I 0 minus to I 0 plus, that is from 1 ampere to 1.125 ampere, and this sudden change will take place, step jump of I will take place at t equal to 0. This step jump will take place at t equal to 0 from at t equal to 0, 0 minus to 0 plus, that is all. Therefore, the solution of this problem will be, if you sketch this current waveform, I should draw it like this. At t equal to 0 minus, the current was 1 ampere, say this is 1 ampere. It was there, this is t equal to 0, this is t. At t equal to 0 plus, this current shoots up to 1.125. So, in no time it goes there. This is 1 ampere, it now goes to 1.125 ampere, and then of course, it will decay like this. Decay of current, this axis is your I t. For me, it does not matter whether it is 0 plus or 0, I mean what is the point. So, so this will be the complete solution of this one. Let us do it for the second problem. Second problem is like this. Suppose you have a differential equation, say d 2 I, d 2 v, say one capacitor voltage something like this, d2v dt2 plus 5v, 5 dv dt plus 6v, and suppose this circuit is energized with an impulse function. It is looking at the equation, it looks like some RLC circuit, voltage across the capacitor. Okay. Recall that in an RLC circuit, RLC series circuit, differential equation will be Ri, and Ri is CV dV dt. Just I am writing this Ri plus L d dt of I, that is C dV dt, and plus of V, and that is the left hand side, and any excitation x t. Now, if this one you write, it will be LC is d2v dt2 plus RC is dv dt, and plus V is equal to x t. You recall this, and then you write it like this, d2v dt2 is equal to R by plus R by L dv dt plus 1 by LC into V is equal to your x t for any excitation to this series RLC circuit series. So, suppose this equation you have set the value of R, L and C such that for this circuit R by L is 5 and 1 by LC is 6, like that. So, anyway, this is the voltage across the capacitor. So, this was the circuit RLC. I want to know the voltage across the capacitor. Here is your x t. We have done so many times. This is R, this is L, this is C. So, the values of RLC are such that R by L is 5 and 1 by LC is 6, and on the right hand side you have the excitation, whatever it is. Okay. This is okay now. Now, in such a situation, I must know what are the initial conditions I must give. So, what is the problem at hand? Problem at hand will be solve for V t for t greater than 0 plus. That way I will be solving. So, and what are the boundary conditions given? Boundary conditions given, there must be two boundary conditions. One is V 0 minus is given, and another is dV dt at 0 minus is given. These two boundary conditions are known, are given to you. Now, for t greater than, so x t if it is equal to delta t, for t greater than 0 plus, the circuit looks like impulse does not exist at that time, and the circuit will look like this. The x t is 0. Impulse only exists. This is the circuit at t equal to between t equal to 0 minus to 0 plus. That is what, because delta t only makes its presence felt during 0 minus to 0 plus. So, for t equal to 0 plus, it is once again 0. Now, there were some initial conditions given to me, and I have to, I will do it because this is second order equation. I will do it from once again fundamental, because I have forgotten how these are related. Anyway, see, it will also tell you what to do, because delta t is there. So, multiply both sides with delta t. So, this was this. So, this was actually d dt of dv dt, is not, plus it was 5 dv dt and it was 6 v, and that is equal to delta t, it was there. Now, what I will do, I will multiply both sides by dt, so that it will become dv dt, it will become 5 dv, and it will become 6 v dt, and that will be equal to delta t dt. Then I will integrate both sides from 0 minus to 0 plus, this one 0 minus to 0 plus, and this one from 0 minus to 0 plus, and this one from 0 minus to 0 plus, and right hand side will become equal to 1. Rotumta? Oh, you are correct. dt I have multiplied. So, this dt will go, this will be equal to d of dv dt. Thank you. Is not? So, I will clean it and write cleanly. So, this term will become d of dv dt. This is the thing. Now, if you integrate this first term, it will become dv dt only, and then upper limit is 0 plus. So, this must be at 0 plus this value minus dv dt at 0 minus. This will be the first term. Second term will be 5 v 0 plus minus v 0 minus. This will be the second term, and is not that, and plus this integral, and v dt, and this is equal to 1. This will be the situation. Now, I told you last time, in a second order situation like this, right hand side delta t, which of these, that is dv dt v or d2v dt2 will have a step jump. V cannot have a step jump. If V has a step jump, then this will be delta t dv d. If V has a step jump, then dv dt must have a delta, and d2v dt2 will be delta dot t, but there is no delta dot t on the right hand side to balance it off. Therefore, only quantity in this expression will have which will have step jump. Step jump will only we will have in dv dt. dv dt will have a step jump, because if dv dt has a step jump, then this fellow will produce an impulse, so that left hand side, right hand side has one impulse only, no delta dot t, nothing like that, delta t, delta t. Therefore, this was the idea to understand what is going on. So, which will have step jump? It is dv dt will have a step jump. V will not have a step jump. Then this integral v dt over 0 minus to 0 plus, this 0 plus 0 minus as small dt becomes so small. So, this will be eventually 0, I mean no point. V cannot have a step jump, therefore, V must be continuous. So, this tells me that V 0 plus must be equal to V 0 minus, since it is not a step jump case. However, dV dt 0 plus will have a step jump from one value to the other. Got the point? Therefore, for t equal to 0 plus, it is a second order system R L C. I want to solve for this V t, and if I know V t, I can differentiate it to get the current C dV dt. So, this current I t, I am interested to solve. I will then say, oh, it is a second order differential equation and no excitation, maybe capacitor will have some initial voltage. Do I know the value? Yes, I know V 0 plus. How much it is? It is same as V 0 minus. This condition is known. Then another condition is necessary. What is that condition? That is dV dt at 0 plus. So, other condition necessary is dV dt at 0 plus. Do I know this value? dV dt at 0 minus is known. So, dV dt at 0 plus will be how much? This side is 1. Na? So, this must have got this. So, dV dt at 0 plus will be equal to 1 plus dV dt at 0 minus. Let me be consistent. So, dV dt at 0 minus. How do I get this? Because this side V 0 plus is V 0 minus, this is 0, this is also 0. So, this term will be also 0. So, this one, so dV dt at 0 plus minus dV dt at 0 minus must be equal to 1 from this equation, So, from this equation dV dt at 0 plus is known. Therefore, now I have a problem where there is no excitation and the initial conditions are known, and I can solve. So, for t equal to 0 plus, for t greater than 0 plus, the circuit was like this. It was shorted, and what was the equation? d2v dt2 plus 5 dv dt plus 6v, and that is equal to 0. This is the solution. So, and what are the boundary condition? Boundary condition is V 0 plus is known, which is equal to V 0 minus, and the boundary condition, because two boundary conditions are needed at 0 plus, will be equal to 1 plus dV dt at 0 minus. These were given to me. So, I will be able to calculate these two. Then the characteristic equation, in this case it will be m plus 3. I am stepping, I am quickly writing this. This will be the characteristic equation. Roots are not equal for this particular problem. M1, M2 will be equal to -3 and -2. This will be the roots, and Vt you can write it as A into e to the power minus 3t plus B into e to the power minus 2t. This equation is valid for t greater than 0 plus no excitation, and then apply these boundary conditions, that is V 0 plus is V 0 minus. So, put that. So, you write V 0 plus whatever is known now will be equal to happens to be V 0 minus is equal to A plus B. This will be one equation, and the other equation will be differentiate this, that is dv dt you differentiate, and this will be minus 3a e to the power minus 3t plus minus 2b e to the power minus 2t. This will be dv dt, and then you say dv dt at 0 plus, it will be equal to minus 3a, t equal to 0, 0 plus and t e to the power minus 3, 0 plus is also 0, 1. So, minus 3b minus 2b, and this value is known to be, because I am giving dv 0 this one, it is equal to 1 plus this value, which is known to me. So, there are now these two equations, solve them, solve for A and B, which I am not doing. You can just try solve them and then come back here and say. So, the important point is, if a differential equation has impulse as its input signal x t equal to delta t, then do not apply that rule, that is final solution will be equal to some natural response plus linear combination of the forcing function. No, that way it will not, you will not proceed. In fact, whatever was derived, we assume that it excludes that impulse function. But anyway, even if impulse function is there, I have now told you how to carry on the calculations to get the response current I t if it is excited by an impulse. And what happens is this impulse only exists around t equal to 0, and in rest of the time it is not there. So, for me to get the solution of the circuit for t greater than 0 plus is good enough, because I do not find any difference for practical purposes between 0 and 0 plus what is there. So, solve for I t t greater than 0 plus, circuit is once again like this. Okay. So, and the circuit was like this, source was really active only during this brief period for t 0 minus to 0 plus, it was active. At 0 minus, as usual, we knew the boundary conditions, then I mean a capacitor is also there. So, I have to recalculate the initial conditions with physical arguments, that is which quantity will have a step jump, because you know in any situations, for example, that is what I told, for example. So, the conclusion will be that if you have any waveform For example, you have a voltage waveform like this. This is suppose -1, this level is -1, this is suppose 2 plus 2, this is also 2, this is also plus 1. A signal goes like this is -2, -2. What I am telling, this is some signal x t. It was -2 for t less than -1, this point is -1. For any negative value of time, this function had a constant value -2. Similarly, between -1 and +1, between these 2 points, it has got a +2, +2. And for time greater than 1, this axis is time, we should not forget to mention that. And then it will have -2 values for t greater than +1. Now, such a function, if I differentiate, time, you see the differentiation of dx dt of this signal, if you differentiate up to -1, this is +1. Before -1 it was constant -2, so differentiation will be 0, that is all. Now, at t equal to -1, I find the signal jumps from -1 to +1 in no time, this change discontinuity -1 to +1. Therefore, it has jumped by a step of 3 from -2 -1 3. Therefore, we must expect there will be an impulse sitting here, dx dt must have an impulse here. Similarly, between -1 to +1, value is constant, dx dt will be 0. And then at t equal to 1, another jump takes place of x t. From where? Plus, I did a mistake, please forgive me. This was -1, so this is also -1. Suppose this level, it could be anything, but anyway, let me write correctly, so that it is. So, this was also, this level was -1, this level. So, -1 to oh, -2 I have mentioned, okay. Oh, there was -1, that is why confusing. So this is also, this -1 I should remove, that is the. So, this level was -2, this is also at -2. So, it is -2, this level. So, here so it was actually -2 to +2. So, the jump has taken place 4 times. So, here will be an impulse whose strength will be 4, and this impulse will have 4 delta, 4, this impulse will have a strength of 4 of delta, and it is a shifted delta function +1. It is not sitting at origin, sitting at t equal to -1. Similarly, here there will be another impulse, but this time it comes down from +2 to -2 in no time. So, its derivative must give you another impulse here, whose strength is 4, -4 is not, final -2, -4 and delta of t -1. So, shifted delta functions you will get. Anyway, so this you keep in your mind. Therefore, we have solved now, we are well equipped to solve differential equations, whether it is a reasonable function x t excitation or it is any impulse present on the right hand side, I will be able to solve for the current classically. Okay. In previous lectures, I told you I have only digressed a bit at that time, telling that you see most of the times functions will be reasonable type like sinusoidal. Then to find out the solution due to sinusoidal functions, we adopted phasor approach to get the solution, at least solution due to forcing function. Okay. Anyway, next class I will start the self and mutual inductances, which are very common in electrical circuit. Okay. Thank you.